Hello everyone, welcome back to Math with Allison. Today we're doing another Calculus 1 final. So this is a real final that was given to students in the spring of 2017. This is now given to current students to study for their upcoming final. So let's go ahead and do this thing. There are 22 questions and here we can see what each problem is worth. So we're going to be putting our work in today. If you want to attempt it on your own, the PDF is linked down below in the description, so you can go ahead and check that out. But we are given some helpful formulas, which is really nice. At the beginning of the page, we have the summation formulas, and we're going to use that for a further problem. So let's go ahead and dive into it. Here we have question 1. We want to compute the following limits. If we use L'Hopital's, we must justify, why we can use it, aka we have to show indeterminate form. So let's go ahead and start off with A. So first, what we want to do is apply direct substitution, right? So I'm going to go ahead and plug in that limit value of t approaching 1. So here we get the natural log of 1, which is equal to 0. So that's a nice way to start off the exam. You just get direct substitution, right? But that's also something that we need to know. We need to know that the natural log of 1 is equal to 0. Here we have a right-sided limit, so the limit as x approaches 2 from the right. We're going to go ahead and try direct substitution, and I'm going to plug in 2, and as we can see, this is going to be approaching 2 divided by 0, which also tells us that this is going to be a vertical asymptote, right? So when we have vertical asymptotes, we know that the limit is approaching either positive infinity or negative infinity. We just want to figure out which one it is. So first, we know that the numerator is approaching a value of 2, right? But let's go ahead and see what our denominator is approaching. It's going to be approaching 0, but we want to see if that's from the negative side or from the positive side. So what I'm going to go ahead and do is I'm going to take a value directly to the right of 2. So let's just take 2.1. When I plug that into the denominator, I get 2.1 minus 2 is equal to positive 0.1. So here I can see I'm approaching 0 from the positive side. So that tells me something about my infinity. It's going to be positive infinity, right? And that right there is going to be our solution. Okay, so here we have another limit. Let's go ahead and try direct substitution. Here we get 3 squared minus 9 divided by 3 minus 3, which we can see is going to be approaching a value of 0 over 0. So there's two different ways we can do this. The first way is your brain might be like, oh, I can factor the numerator because it's a difference of squares. And the purpose of doing that is so that the x minus 3 divides out, and all we're left with is the limit as x approaches 3 of x plus 3. And again, we can go ahead and apply direct substitution here. So we can plug in that 3 value, and we get 3 plus 3 is equal to 6. And that right there would be your solution. The other way that you could do it is we've shown indeterminate form, right? It's going to be right here. And so we can go ahead and apply L'Hopital's rule. Here, I take the derivative of the numerator, get 2x divided by 1, and then I can apply direct substitution. It's just 2x, right? So I get 2 times 3, which is equal to 6. So here we get the same solution either way. There's no better way to do it. Both ways are totally correct. It's just going to be whatever your brain sees first. If I were doing this, I would probably see, oh, I can factor it. But other people's brains are different. Okay, here we have some more limits. We have the exact same rule. So let's go ahead and try to do this thing. Here we have a limit approaching infinity. So again, there's two different ways you can do this. The first way you can do is you can take the highest power of both the numerator and the denominator. So I'll go ahead and rewrite that. The only time we can do this is with a limit to infinity because we're working with such large numbers. So if this was like approaching 2, we would not be able to use this trick. But here we can go ahead and simplify it. And here we just get a value of 1/3. Another way that you can do it is, of course, using L'Hopital's. This is obviously going to go to infinity divided by infinity, which is a form of indeterminate form. So here I can go ahead and apply L'Hopital's, and I'm going to take the derivative of the numerator and the denominator, right? So I get 2x plus 2 divided by 6x plus 2. So here, if I were to apply direct substitution again, I get infinity divided by infinity, which tells us this is indeterminate form, and we can once again apply L'Hopital's. So here when I do that, I get 2 divided by 6, and of course this simplifies to just being 1/3, right? When we take the limit of a constant, it's just equal to that constant. And we would get the exact same solution either way. So again, whichever your brain sees first, just go with it. Okay, so now we have the limit as x approaches 0, so we can't use the trick we just learned, which is fine because our function's a little different. But let's go ahead and try direct substitution. So we get sine of 0, pi times 0, 0, divided by 0, which goes to 0 over 0. So this is once again indeterminate form, right? And so we can go ahead and apply L'Hopital's. I like to indicate that I'm applying L'Hopital's just for my grader. So here the derivative of sine is cosine of pi x, and then we have to multiply by the derivative of the inside, right? I'm doing chain rule. Multiply by pi, and this is divided by 1. So let's go ahead and try direct substitution once more. So we get pi times cosine of 0 divided by 1. I mean, that doesn't change anything, but we get pi times 1 because cosine of 0 is 1, and this just turns into pi. And there we have our solution. Okay, so here we want to find the horizontal asymptotes of f. So the horizontal asymptotes occur at the end behavior, because if I did a little graph right here, let's say we have a horizontal asymptote right here. That means our function is approaching it, and this would be the limit as x approaches infinity, right? Because it goes on forever and ever. So we do the same thing when x is approaching negative infinity as well. So here, let's go ahead and take the limit as x approaches positive infinity of our function, and the same thing of negative infinity. So since we're working with limits at infinity, we could either take the highest power of both the numerator and the denominator, or if you wanted, you could plug it in. We get indeterminate form, and you could apply L'Hopital's rule. So I'm going to let you guys try L'Hopital's if you want, but you should get the same solution as I'm about to get right here. Okay, so here I got 5/4, and if you applied L'Hopital's, you should also get 5/4. And this tells us that we have a horizontal asymptote, so I'll say y is equal to 5/4. Remember, if it's a horizontal asymptote, it stabs the y-axis, which means we're going to have y equals. And that's our solution for part A. And now for part B, we want to go ahead and find vertical asymptotes. So vertical asymptotes are where the denominator is equal to 0, but we have to be careful because any terms that divide out are going to be functional wholes, not vertical asymptotes. So don't just factor the denominator. We also want to factor the numerator. So let's go and factor the whole thing. In the numerator, I'm going to go ahead and pull out x, right? So we get 5x minus 1, and then divided by, and here we can take out a 2, so we get 2x squared minus 1. So let's go ahead and factor out the denominator. Okay, so I see that none of these terms are going to cancel out, and so I don't have to worry about any functional wholes. So if you don't remember how to factor out the denominator, what you could just do is straight up set it equal to 0. Because if I can just look at it from this first factored form, I can see that nothing's going to divide out, right? So we can just take 2x squared minus 1, set equal to 0. So here I get 2x squared is equal to positive 1. Divide by both sides by 2, I get 1/2. And here I can take the square root of both sides, right? And I get positive and negative square root of 1/2. And if I were to set this denominator equal to 0, I would end up with the same solution, right? I'm not sure how you would need to write this out. Sometimes they ask you to prove it. In this question, it's not asking us to prove it, but you could say, as x approaches positive and negative square root of 1/2, f of x grows infinite. That could be additional, whatever. So here, determine the value of the constant h for which the function is continuous. So here we have this whole function when x is not equal to 1, and then we have a value of a when x is equal to 1. So what this is asking is we have a function something like this. It's nice and continuous until we hit that value 1, and then it continues on. So if we want the entire function to be continuous, we want a to be whatever this value is going to be, right? So we take the limit as x approaches 1 of our function, x squared plus x minus 2 divided by x minus 1. So here what you can do is you could either try direct substitution to make sure, this is going to equal something. So we get 1 squared plus 1 minus 2 divided by 1 minus 1, and we can see this is going to approach 0 over 0. Since this is a final exam, you could apply L'Hopital's, and I'll let you guys do that if you did. Otherwise, what I would do is I would factor, because I think that's what my brain would see first. So here this factors into x plus 2 times x minus 1 divided by x minus 1, and that's very nice because the x minus 1 divides out. And so here we're just left with the limit as x approaches 1 of the x plus 2. Here we can go ahead and try direct substitution now, and we get 1 plus 2 is equal to 3. And so this tells us that we want a to equal 3. And it doesn't say that we have to explain why, it just says to find the value of a, so I believe that we're done. If you applied L'Hopital's, you should also get a value of 3. Okay, so we're moving on from limits. We're going to go ahead and do some derivatives. So let's go ahead and do this thing. So first, that constant multiple hangs out, and the derivative of sine is cosine of x minus the derivative of e to the x is e to the x. Very nice. Plus, and let's use power rule, 7x to the power of 6 minus, and let's go ahead and rewrite 1 over x. We can rewrite it as x to the negative 1. So we bring down that power, and we subtract 1 from the current power. So if you wanted, you could rewrite that, but I would also say with this professor, you'd be perfectly okay to leave that answer as it is, because this becomes 1 over x squared. If I'm a grader, I'm going to recognize either way, right? So then that's the first solution. Oh, now right here, I notice that we have a product, right? We have a product between x cubed and the natural log of 2x. So that cues me in. I'm going to go ahead and use product rule, and I'll go ahead and set that up for those who like to visually see it. Okay, so first for our f prime, we're going to get 3x squared just using power rule. And now we're going to use the natural log rule. So whatever's on the inside of the natural log goes on the bottom of the fraction, and its derivative goes on the top. So the derivative is just 2, and this simplifies to 1 over x. So let's go ahead and multiply. So first I'm going to start from the bottom, work my way to the top. So I get 3x squared times the natural log of 2x plus, and I'll work from the top to the bottom. So that's x cubed times 1 over x. If you wanted to simplify, I'm sure you could, but again, we would be perfectly happy if you left it like that. But I do not speak for your professors. I don't know what you guys would like. But you could go, that far. Okay, here we have one more, and as we can see, if you recognize it, this is going to go ahead and be quotient rule. So I'll go ahead and set that up. Okay, so here we get f prime is just equal to 1, very nice, and we get 1 plus x squared, that derivative is just 2x. So this is where order does matter, which is why for the product rule, I do the same order so I don't forget it. But we start at the bottom, work our way to the top, so we get 1 plus x squared, because that's just multiplied by 1, and we subtract from the top to the bottom. So we get x times 2x, and all of this is being divided by 1 plus x squared, quantity squared. So if your professor likes you to simplify, 1 plus x squared minus 2x squared divided by that denominator. And actually, we can simplify that one more time, right? We get 1 minus x squared divided by that whole thing. So like I said, if you were in our class, that would look beautiful. If your professor said to simplify, that would look beautiful. If you just want to simplify, great. But sometimes when you continue simplifying, you have more room for error, which is why we tell our students to just kind of leave it. But again, it depends on your teacher. Well, here we have some more derivatives. Ooh, inverse sine, everybody's favorite. So I'm going to go and write down what that derivative is. So that's the derivative, and it's going to be a little different with x squared. So what happens is, let's go ahead and do the derivative of the outside first, because this is going to be chain rule. So we get 1 over the square root of 1 minus, and instead of x squared, it's going to be whatever's on the inside squared. So x to the power of 2 squared. But now we have to multiply by the derivative of the inside. So we have to multiply by 2x. So if you wanted to simplify that, that 2x can go in the numerator, and we get the square root of 1 minus x to the power of 4. And that right there would be our solution. So here, I'm going to go ahead and rewrite this first. So we are taking the derivative of e to the x to the power of 1/2. So if you remember e rules, I like to remember it like a triangle. First, what we do is we drop it down. So that doesn't change at all. But now we multiply by the derivative of whatever the exponent is. So here we get 1/2 x to the negative 1/2 times e to the x to the 1/2. And if you wanted to rewrite that with all the radicals, we get 1 over 2 to the square root of x times e to the square root of x. Or again, you could rewrite it like this. And any of those solutions along this line would be okay for us. We have a function defined on negative 2 to 2, and we want to sketch the first derivative. So first, let's notice how our function is decreasing. That means our derivative is going to be somewhere in the negative zone. But we quickly switch to a critical value, right? This is where our function is neither increasing or decreasing. And then our function finally switches over to increasing, which tells us our function is going to be somewhere in the positive area. So our next step is to try to figure out what the slope is. So I know at 2, we have a slope of 0. So I know for sure I'm going to have a point right there. And let's go ahead and look at the endpoints now. So if I were to extend this line out, like I was just extending the tangent line, here I can go ahead and estimate what the slope is going to be. So if I start at negative 2, I go up 2, and I go over a value of 1, right? Because that would be 3, which tells me I have a slope of 2. So that was right here at this point, I have a slope of 2. So I went up to that 2 value. And now if I were to do the same thing on the other side, here if I extended out the tangent line, I would have something super similar, right? I'd go up 2, but I would go to the left 1. And so here I would have a slope of negative 2, right? So here this helps me connect all the dots. I'll go ahead and erase this stuff. And here this would be my derivative. If you also can guess that because we're looking at a quadratic function, the derivative of a quadratic is always going to be linear, then we know we have a straight line and you can work from there. Oh, here we go, another graph. So we have the graph of the first derivative. So this right here is f prime of x. And we want to go ahead and fill in parts a, b, and c. So according to the derivative, on what intervals is f decreasing? And so this is going to be wherever our first derivative is negative, right? So it's going to be these values. We have to be very careful not to include the critical values. So we have 3 critical values right there. So here, what I would do is I'd go from -2 to 0, union 0 to 2. I cannot include 0 because 0 is a critical point. That's where a function is neither increasing nor decreasing. What values of x does f has a local maximum? So a local maximum is where our first derivative changes from positive to negative, right? And so here I can see where we're positive, which is going to be on these 2 endpoints right here. And now we have to work left from right. So here I can see that my first derivative changes from positive to negative. And then on my other side, we change from negative to positive. And you can think of it like we're increasing, we're decreasing. So we get a local maximum. So this is going to occur at x equals -2. And I'm going to assume that this is supposed to be a minimum. And this is going to be where a function changes from decreasing to increasing, right? So we have a local minimum like that. And that's going to be at x equals +2. So we're just going to pretend that's a minimum. We're in the graphing phase, I guess. So we're going to go ahead and graph the function given the following information. So they give us 3 x-intercepts, which are already indicated on the graph right here. And we want to go ahead and satisfy these terms about the first and second derivative. So first we have that the first derivative is positive, which tells us that f is increasing. So I'm going to go ahead and take my value of 3 and between -3 and 0. So I'm also going to put these 2 on here. This is how I do it. If you guys have another way of doing it, that's totally great. But I like to write underneath what's happening. So when x is greater than 3, our first derivative is positive, which tells us our function is increasing. So I'm going to be increasing right there. And between -3 and 0, my function is going to be increasing. Okay, and now our function is less than 0 when x is less than 3, -3. So here I'm going to be decreasing, and also between 0 and 3. So here I'm also decreasing. Okay, so we did the first one, we did the second one. Let's see, our next one's about concavity. So this is going to be between -2 and 2. So I'm going to go ahead and draw those in. So the second derivative is positive, which means that it's concave up when x is less than -2. So that's going to be concave up right here when x is less than -2, and when x is greater than 2, so it's going to be concave up on this side. Okay, and then we have that the second derivative is less than 0, aka concave down, between -2 and 2. So right here, it's going to be something like this. Okay, so first we're going to be decreasing and concave down. So we have something like this all the way until we hit -3. But then we switch to increasing and concave up, but then at -2 we switch to concave down. So we have to do something like this, concave down. We switch over again to concave up, but we're still decreasing, and it would look something like that. That's a terrible drawing, but good enough, right? So the area of a circle increases at a rate of 1 centimeter squared per second. So I'll go ahead and write that down. So we have the derivative of the area in terms of t is equal to 1. And I know that because the area is increasing at a certain rate, which means it's the rate of change, right? The first derivative. Then we have how fast is the radius changing. So we're finding dr dt when the radius is 2 centimeters. So here we have that the radius is equal to 2. And also, oh, they give us a nice little formula. How kind. And they give us that area is equal to pi r squared. So we're already working with one variable, so we don't have to do any substitutions. But of course, we're going to go ahead and take the derivative of both sides in terms of t. So first, we get the derivative of the area in terms of t is equal to, pi is a constant multiple, so it hangs out. And now we can take the derivative of r squared. So we get 2r times dr dt, right? Because we can't take the derivative of r in terms of t. They're 2 different variables. So let's go ahead and fill in what we know. We know dA dt is equal to 1. And that pi stays the same, or you can rewrite that as 2 pi. And we have that the radius was equal to 2. And then we wanted to find, and we can look back at the question, how fast the radius is changing. So dr dt. So let's go ahead and solve for that. First, we can go ahead and multiply 2 by 2. And then we can go ahead and divide it over, or you could have done that all together in the next step. Depending on your professor, you might need units, and so in this case, it's going to be centimeters per second. And there we have our solution. So here we have a function, and we want to go ahead and find the critical point. So we're going to be applying the first derivative test, which means I want the first derivative. So the first thing I'm going to go ahead and do is rewrite this. So this is negative x squared minus 16x to the negative 1. So I can clearly see power rule, right? So we get g prime of x is equal to, and that becomes negative 2x plus 16x to the negative 2, which again, we can go ahead and rewrite as 16 divided by x squared. So our next step in the first derivative test is to set this equal to 0 in order to solve for those critical values. So I'm going to add over 2x, and I get 16 divided by x squared is equal to 2x. I can multiply both sides by x squared, so I can get that out of the denominator, and I get 16 is equal to 2x to the power of 3. Go ahead and bring that up here. I'll divide both sides by 2, so I get 8 is equal to x to the power of 3. And here we can go ahead and take the cube root of both sides. And here we get 2 is equal to x. And we don't get positive or negative 2 because it's not the square root. So that's our solution. So now we want to find the intervals on which our function is increasing or decreasing. So I'm going to go ahead and set up our number line, right? So here we plug in our critical value, which is 2. And we're going to take test points from each interval, plug that into our first derivative. And that tells us if it's positive or negative, if our actual function is increasing or decreasing. So also when we're doing our number chart, we have to pay attention to illegal values. So let's go ahead and take a look at our first derivative. If I were to look for an illegal value, I would see that we have 16 divided by x squared, and we cannot divide by 0. So we also have to make sure to include that value 0. So now that we have all our critical values filled in, so now that we actually have all of our critical values, I'm going to go ahead and take test points. So I'm going to do negative 1, let's do positive 1, and 3. So now that I'm trying to plug in 3, I realize it's not going to turn out very nicely. And actually, if I chose 4, it would be a bit nicer. Yeah, that was much nicer. Okay, so here when I plugged in a value of negative 1, I got a positive value, which tells us that our function is going to be increasing on the left side of 0. Then when I plugged in 1, I also had a positive value, which tells me we're going to continue increasing on the other side of 0. And then when I plugged in 4, I finally got a negative value, which tells us our function is decreasing. So here we want to find the intervals on which our function is increasing or decreasing. And there I have my intervals, right? We have to make sure to not include 0 because 0 is where our function is not defined. So we can't include that as an interval of increasing or decreasing. Okay, so now we're going to go ahead and use the first derivative test to determine which is a local maximum, a local minimum, or neither. So here we have at x equals 0. It is neither, right? Because a local minimum or maximum has to occur where the derivative changes from positive to negative or negative to positive. And here it doesn't change. It's just positive and positive, right? But then at x equals 2, we have a maximum, right? Because we can see that as our function first derivative changes from positive to negative. Okay, complete the following steps to calculate a Riemann sum. So here we have f of x equals negative x plus 8 on the interval 0 to 6 with n equals 3, which tells us we're going to have 3 equal subintervals or 3 rectangles. So we're going to first sketch a graph on the function. So here, just looking at my function, f of x equals negative x plus 8. That tells me I have a y-intercept at 8, right? That's going to be right there at that point, and then I have a negative slope of negative 1. So there I went ahead and drew the graph. Make sure to label the axis. Okay, this is x. This is f of x. So this right here is going to be 6, 2, 4, 6, 8. Okay, I labeled it. I labeled it some more. Okay, we're going to go ahead and find delta x. So delta x is equal to b minus a divided by n. So it's going to be 6 minus 0 divided by 3, which is equal to a value of 2, which tells me each of my rectangles are going to be a distance of 2. So if I fill that in, I can see right there, those are going to be my little subintervals. So that helps me find my left-hand endpoints, x0, x1, and x2. So x0 is going to be the first left-hand point, which is 0. x1 is going to be the second one, which is 2. And then x2 is going to be that last one, which is 4. We're going to illustrate the left Riemann sum, and I'll go ahead and draw those in. So first we're going to have the left one, which is going to go up to here. And here we have our first rectangle. Our second one is going to be f of 2, so we're going to go up to the function and then fill that in. And then our last one, f of 4, go up to the function and we can fill that in. So here we're going to go ahead and calculate the Riemann sum. So if you wanted to, you could plug it into the function, or you could just do it by, counting squares. Each of these rectangles has a little width of 2, and we're going to go ahead and see the corresponding height. So this has a height of 8, this has a height of 6, and this has a height of 4. So if we were to calculate those, we would get 8 times 2 plus 6 times 2 plus 4 times 2. And this is equal to a value of 36. And there we calculated the Riemann sum. Okay, so we're going to evaluate the following expression. And I went ahead, this was from the front page of our exam, and I just, reposted it. So that way we can go ahead and apply it. So our first step actually is to try to simplify this inside so we can get some of this k squared, k stuff going on. So let's go ahead and do that. So the nice part of summations is that it's very similar to like derivatives and integrals, is that we can go ahead and split it up. So we get k squared plus. And then another thing is that constant multiples just hang out, so we can bring those outside of the summations. Okay, so now let's go ahead and apply these formulas. So first we have k squared. So what we do is we take whatever our n value is, and for us that's 99, and we plug it in everywhere we see an n. So I'll go ahead and do that. Here for k, I'm going to do the same thing. So I get, and here we have the summation of 1 of 99. So we're adding 1 99 times. We end up getting 99. And I would expect you guys to just leave it right here. If you wanted to simplify it further, go for it. I'm not going to. So here we have a figure of the regions bounded between f and the x-axis on the interval -4 to 4. Here we want to go ahead and compute the following integral, -4 to 4 f of x dx. So we're going to be starting right here, and we're going to be ending right here. So let's go ahead and calculate these areas. First, I can calculate this little guy just by using the area of a triangle. So here we have a width of 1 and a height of 2. So I get area is equal to 1/2 base times height, right? So this first little guy has an area of 1. I can calculate this next area, and it's the exact same triangle, right? But we're below the x-axis, which tells me that this is going to be -1. Next thing I'm going to do is this entire rectangle. We got a nice little rectangle in there, and I'm going to continue using geometric methods. So this has a base of 4 and a height of 2, and technically that's -2 because we're still below the x-axis. So this is -8. And then we have one more little triangle in here. It's going to be this guy right here. And again, we can do 1/2 base times height. The base is equal to 2. The height is -2 because we're below the x-axis. So this has an area of -2. So now what we do is we add all of these together. So this is equal to +1 plus -1 plus -8 plus -2. These guys cancel each other out, and we're just left with -10. And that right there is our solution. Okay, now we're moving on to integrals. So here we have indefinite integrals, and we want to go ahead and evaluate them. So my first thing is I'm not going to try to do that yet. I'm just going to rewrite it so I can see power rule really clearly. I didn't use power rule on that last one because that's going to be a natural log thing, right? So here, let's go ahead and take the antiderivative. So I add 1 to the exponent, divide by that new exponent. Do the same thing right there. And that scalar multiple hangs out, but that becomes the natural log of x. And don't forget some constant c. So if you wanted to simplify this, you can. So we get 3 times 2/3 x to the 3/2 plus 1/2 natural log of x plus c. And here we notice that those 3's cancel out. That's just nice. And then right there for natural log, I use the power rule, so that becomes the power. But I would say that's pretty good. Here we're going to go ahead and compute another derivative. So here we have the antiderivative of cosine is going to be sine of t minus, and the antiderivative of secant squared is tangent of t plus some constant c. If you want to check your work for either of these, what you would do is you take the derivative of their answer, and whatever you get for the derivative should be whatever you were trying to originally integrate. So that's a great way to check your work if you have extra time. Okay, we have more indefinite integrals. So for this first one, I see that I have a product. So actually what I'm going to go ahead and do is just multiply them first, right? I don't see anything for u-substitution because both of these are just normal x's. There's no powers, there's nothing. So I'm just going to multiply. And here we can just go ahead and take the antiderivative. So that 11 hangs out. We add 1 to the power, divide by that new power. 3 hangs out. We get x cubed divided by 3. when we have a constant, we just tag on that x value, and then don't forget c. And actually, that one simplifies. So if you wanted, you could do that. 11 halves x squared minus x to the power of 3 plus 4x plus c. And that right there is our final solution. Now we have another one. And again, I see that if you wanted, you can simplify it first. We're just working with normal t stuff. So here we get 3t squared divided by 5t plus 4t divided by 5t. And that right there is much simpler to take the antiderivative up, right? So here we get 3/5 times t squared divided by 2, and then that becomes 4/5 t plus some constant c. If you wanted to rewrite it, you could. 3t squared divided by 10 plus 4t divided by 5. They're equivalent. Either answer is going to be totally great. Okay, now we're going to do some velocity stuff. So here we have the acceleration of gravity. Oh, they're very kind. They round it up for us. I know it's not super accurate, but when you don't have a calculator on an exam, -10 is nice. So here we're going to find an expression for the velocity as a function of time. And we are given some initial conditions. So our first initial condition is that at t equals 0, the ball is popped up vertically from the ground with a velocity of 30 meters per second. So this tells me v of 0 is equal to 30. And that's our initial condition that we're going to use in order to find the velocity function. So v of t, our velocity function, is equal to the integral of acceleration, so of -10 dt. When I do that, I add on that t and some constant c, and now we're going to go ahead and use the initial condition. So t is equal to 0, v of t is equal to 30. So here I get 30 is equal to -10 times 0 plus c, and here we get 30 is equal to c, and we can plug that in to get our official equation, which is that. So we found an expression for the velocity of the ball as a function of time, which was just a fancy way of finding the equation. And now we're going to find an expression for the height. And here we have that the ball is popped up vertically from the ground, which means that our initial position is going to be s of 0 is equal to 0. It's impressive to hit the ball from the ground, but we're not going to question it. So here, in order to find position, s of t, we want to go ahead and integrate our velocity function, so -10t plus 30. And we're integrating this in terms of time. So here we get -10t squared divided by 2 plus 30t plus some constant c. And we can simplify that one time. That becomes -5t squared. And now we're going to go ahead and use our initial condition. So we get 0 is equal to -5 times 0 squared plus 30 times 0 plus c. And this tells us that our c value is just equal to 0, right? Because we're starting from the ground. So we can fill this in for our official equation. And plus 0, I don't really need to write. And there we have our position function. Okay, at what time after the ball pops up does it hit the ground? So this is saying at what time is our position function equal to 0? So the first thing I'm going to do is divide everything by -5. There's not a specific order you need to follow for this, but I'm going to go ahead and factor out of t, and I get t minus 6. And here I get two values. So t is equal to 0, which makes sense because that's when it's first on the ground, right? And t is equal to 6. And so this must be the time when it hits the ground. And we can check for units, and we're working in meters per second. And so this is going to be second. And that right there is our solution. So let's go try problem 18. Ooh, definite integrals. Ooh, 1 to 0. Okay, so here when we first take the antiderivative, that 3 hangs out, and the antiderivative of e to the x is e to the x. So that stays the same, but we're evaluating between 1 and 0. So let's go ahead and do upper minus lower. We get e to the power of 0 minus 3e to the power of 1. So e to the power of 0 is just 1, so we get 3 minus 3e. And that's our first solution. Let's go ahead and try b. So we have 1 to 8 of x to the -1/3. So let's go ahead and take the antiderivative first. We add 1 to the exponent, so that becomes 2/3. And we divide by that new exponent, and this is being evaluated between 1 and 8. If you wanted to rewrite that first, we could. So this becomes 3/2 x to the 2/3 between 1 and 8. So let's go ahead and do this thing. So we can actually simplify this. 1 to the 2/3 is just equal to 1. So this whole thing is just equal to 3/2. And now for the other one, I'm going to go ahead and rewrite it for us. Hopefully that makes a bit more sense. So here we get 3/2, and the cube root of 8 is equal to 2 squared minus 3/2. And I'll continue simplifying this. And there we get our solution, or if you wanted, you could just say 4.5, whatever you like to say. but here we get a value of 9/2. Okay, so we have the derivative of an integral. So this is the fundamental theorem of calculus. So we're taking the derivative in terms of x of the integral 5 to x of that whole thing. So what that means is that we just plug in x everywhere we see a t. So we get x squared plus x plus 1. And that right there is our solution. Now, what happens when we're integrating from x to 1 is we want to go ahead and negate it because we want that x to be on top. So we get 5 to x of t squared plus t plus 1. And now we can go ahead and plug that in that rule. So that negative hangs out and we get x squared plus x plus 1. So be really careful on stuff like that. That x needs to be on top. So now we have here that x is on top, but we're x squared. So what's not going to change is we're going to plug in that x squared everywhere we see a t. So we get x squared to the power of 2 plus x squared plus 1. But the difference is since we're not working with x, the derivative of x is just 1. The derivative of x squared is 2x. So what we're doing right here is we're multiplying by 2x. So if you wanted to rewrite that, you could. And we get x to the power of 4 plus x squared plus 1. And I'm not going to simplify that more. You guys obviously can. And that is our solution. So I'll go ahead and write out what formulas I'm doing. So those are the two formulas that I'm employing in this. It has to do with the fundamental theorem of calculus. I'm not going to prove it right here because this is just an exam. But if you want to look more into it, you can. Okay, problem 20, we're going to use symmetry of the properties of integrals to evaluate or help evaluate the following expressions. So here, notice that we have an integral from 5 to 7, but then we switch over an integral from 7 to 5. So what I'm going to go ahead and do is use a property on that second integral. So when I flip the bounds for that second integral, it makes it negative. So instead of plus, this is going to be a minus. And the purpose of doing that is so that they cancel out, right? And that's just equal to value of 0. So if you're sitting there thinking, I don't know how to integrate this, see if there's a way that you can manipulate it using the properties of integrals. Here we have another integral. So the first thing I'm going to do is split it up. So we have negative pi to pi of 1 dx minus negative pi to pi of sine cubed of x dx. So what I notice right here is that this is an odd function. And what I mean by that is that f of negative x is equal to negative f of x. And you can go ahead and plug it in to test it, but it is going to be an odd function. And when we have the same bounds, so negative pi to positive pi, that means the integral of negative a to a of the odd function, that whole thing is equal to 0. And so now what we have left over is just this first integral. So if you wanted to straight up integrate it, you could. Or you can talk about how 1 is an even function. And what I mean by that is that f of negative x is equal to f of x. No matter what we plug in, we're going to get a value of 1. And so you could rewrite this as the integral of 2 times 0 to pi of 1 dx. So either way that you integrate it, you're going to end up with the same solution. So I integrate this, I get x between 0 and pi, and here I can plug in upper minus lower, so pi minus 0. And here we get 2 pi. And that right there is our solution. So we're going to use change of variables, u-substitution. That's very nice of them to indicate that for us in order to evaluate the integrals. So the first thing I notice on this one is that we have a big power. Usually with a big power, we want to set the inside equal to u. So let's go ahead and take the derivative of both sides in terms of x. We get 2x, and I'm going to solve for dx. Okay, and let's go ahead and plug things in. This is an indefinite integral, so I don't need to change any bounds. We get u to the power of 10 times 2x times du divided by 2x. That's very nice of them. That 2x divides out, and we have just the antiderivative of u to the power of 10 du. So here I add 1 to the exponent, divide by that new exponent, add c. We are not done. Make sure to replace u back in. So we get x squared plus 1 all to... I said it, but I didn't write it. X squared plus 1 to the power of 11 divided by 11 plus c. And there we have our final solution. Sorry, my handwriting is getting messy. So here we have x times e to the negative x squared. Usually when we have multiple x values going on like this, and in the last one we saw a big power. I don't see a big power in this one. I want to look for descending powers of x's. So here I have x squared and an x. And I see that descending power. So here I'm going to set u equal to negative x squared. I'm setting it equal to the whole exponent because that negative is just a scalar multiple. Doesn't make much of a difference. You could set it equal to x squared and you would end up with the same solution. So do it either way. So du dx is equal to negative 2x, and I'll go ahead and solve for dx. So this is not a definite integral. We don't need to change any bounds. But here that x we didn't do anything to, but we made the power u. And then we solved for dx, which is equal to du divided by negative 2x. So this is very nice that x's cancel, that we can see. But that negative 2 is still there. So I'm going to bring it out because it's a constant multiple. And I get negative 1/2 e to the power of u du. So here, when I take the antiderivative, it doesn't change at all, right? Derivative of e to the u is e to the u, and antiderivative of e to the u is e to the u. But we have to add on some constant c. And our last step is to replace u back in, so we get e to the negative x squared plus c. And that right there is our final solution. If you did u was equal to x squared, you would still end up with the same solution, which is super cool. Last problem. Oh, now we're doing u-substitution with definite integrals. How many do we have? We have 2. Okay, we can do this, people. Okay, so notice here that I see a power. It's not a very big power, but when we have sine and cosine, look for the one that has a power instead of equal to u. Of course, it's not going to work every time, but it will work some of the time, and that's always nice. Now we're taking the derivative in terms of theta, so make sure you change that to du d theta, but that's equal to cosine of theta, and let's go and solve for our du. Okay, so we found what d theta was equal to, but now we actually do have to change the bounds. So we have the upper bound, theta is equal to pi over 2. We already know what u is equal to. It's equal to sine of theta. So what we can do is we can plug that in. U is equal to sine of pi over 2. And this right here is going to give us a value positive 1. Now our lower bound, theta, is equal to 0. So we get u is equal to sine of 0, which is very nice. That's just equal to 0. So let's go ahead and change our integral. So we have new bounds between 0 and 1. We set sine equal to u, so that becomes u squared, times cosine of theta, times du divided by cosine of theta, and that works out very nicely because that cosine of theta cancels out, which is what we want to happen. And now we have a new definite integral, 0 to 1 of u to the power of 2 du, which to me, that looks way nicer. So first we take the antiderivative, we add 1 to the power, divide by that new power, and we're evaluating this between 0 and 1. So here we don't need to plug u back in because we already changed the bounds and we can just straight up integrate it. So here we get 1 to the power of 3 divided by 3 minus 0 to the power of 3 divided by 3, and this is equal to 1/3. And that right there is our solution. Okay, so this is more of a recognition problem. I can see that this is going to look like inverse tangent, but it's a little different. So I'm going to go ahead and rewrite it so we can see that. And so notice here that we have 2x inside of the squared instead of just a normal x. So that helps me. I'm going to go ahead and change that to u. And I'm going to take du in terms of x. Okay, I found what dx is equal to. Let's go ahead and change our bounds. So our upper bound is equal to pi over 8. And now we can go ahead and plug that into u. So u is equal to 2 times pi over 8, which is equal to pi over 4. So our new upper bound is going to be pi over 4. Our lower bound is equal to 0, and that's not going to change at all, right? Because we have 2 times 0, which is equal to 0. So let's go ahead and rewrite our integral. So that du divided by 2, if you want, you can take it out. It's a constant multiple of 1/2 between 0 and pi over 4 of 1 over 1 plus u squared du. And here we can go ahead and take the antiderivative, right? So that 1/2 hangs out, but we get inverse tangent of u evaluated between 0 and pi over 4. Here I'm going to plug in upper minus lower. An inverse tangent of 0 is just 0, so here we get our solution is this guy right here. And we completed the exam. So this one was a doozy. It was quite large, but the students in this class have 3 hours to complete it, so they do have a good amount of time. But you might be brain dead after. But that's all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlists or link down below. Otherwise, please give this video a thumbs up and comment other problems or topics that you'd like to see done. I think we're officially going to launch Calc 2 soon.